All right, so in this next series of slides, we're going to be introduced to this idea of the normal curve, and it builds off this concept of the probability theory. So frequency distributions, when we were first introduced, and I showed you a couple different ways that a curve can be drawn around our data distribution. We were introduced to kind of three different ways that we might see a distribution represented in graph form. So the most common frequency distribution of what we observe happening is called the normal distribution. And most values in a frequency distribution tend to fall around the center of the distribution or around the mean. Now in this first image here, this first normal distribution that we have on the right, this dotted line down the center is intended to be the marker where the mean exists. Okay, so keep that in mind. In skewed distributions, we have measures of central tendency, so mean, median, and mode, that are in different positions. And this graph, these graphs really should look familiar. I pulled them directly from our Module 2 frequency distributions. In this second set of graphs, we have two different types of skewed distributions, right? Remember that in a skewed distribution, we're talking about measures of central tendency that are at different areas, right? So in our first graph on the left, our positively skewed distribution, we have a mode and a median and a mean that are all found at different points within the distribution. Same thing to be said about the negatively skewed data distribution. And finally, we learned about symmetrical distributions. And in symmetrical distributions, you have a mean and a median that are found at the center of your distribution, but there may be a varying number of modes. So you might have no mode, you might have one mode, two modes, three or more. And so in the example of symmetrical distributions, remember that when we talk about what is symmetrical is that we can draw a line down the middle, take what's happening on one side, flip it over to the other, and have an exact replica, right? It's perfectly symmetrical, or it's, I shouldn't say perfectly symmetrical. It is symmetrical such that what's happening on one side can be understood as happening on the other side. So the purpose of the curved line, some of you may be wondering, well, why do we incorporate this line around the data distribution? And there are a couple reasons why in terms of what they mean or what they represent for principles of probability theory. What I want to focus on primarily is that the goal or the intention of the curved line is to help us understand that all of the data points in our distribution are found underneath the curved line. Okay, the curved line always sits above our data. It's always intended to represent that all of our data exists underneath that curved line. All right. Gonna apologize. I need to sneeze. Okay. Now that I figure out how to pause, I'm going to be pausing all the time. Here we go. Let's move forward. Okay, so the normal curve and its characteristics. This is particularly important because anytime we're discussing the normal curve, especially in terms of probability from here on out, I need you all to understand these really important characteristics about the normal curve. Now notice that in this normal curve that we have on the screen in this PowerPoint, we have a line drawn down the middle. I want you to remember that that line represents the mean. All right, we have the mean drawn right at the middle, and then we have sigma, which represents standard deviation. Now in this particular image, a portion of this normal curve is shaded. I want you to ignore that for just a moment. We are going to come back to that to kind of discover what that means and how it relates to normal curve. But here are some important characteristics that we need to make sure we understand. So the normal curve is a theoretical ideal, right? So it's based on probability theory. This is what we should see happen with an unlimited number of observations. That wasn't something that I mentioned before, this idea of an unlimited number of observations, but that's kind of what makes this difference between probability distributions and frequency distributions such an important kind of theoretical principle. In frequency distributions, we're talking about what we are observing occur. This is, data we've collected. But probability distribution is based on an unlimited number of observations. And in reality, we can never have an unlimited number of observations of anything, right? And so with that, that's kind of part of why this, understanding how the probability distribution differentiates from the frequency distribution is so important. So here are the characteristics that as you are hopefully taking your notes based on this, I want to make sure that you all understand. So in this case, the normal curve is symmetrical. Okay, whatever's happening on one side of our distribution happens on the other. In this case, we can imagine that the line where this mean is drawn, imagine that we make a cut right at that point, and we can take what's happening on the left side of that cut and flip it over onto the other side, and it would perfectly match what's happening on the right side. The normal curve also is unimodal. As a reminder, unimodal represents a data distribution having only one mode, right? So only one measure of central tendency or one mode as a measure of central tendency. The normal curve has all measures of central tendency located right at the middle. They are all the same number, okay? And then finally, the highest frequency. Remember that when we first were introduced to mode, we're talking about this idea of a piece of data that happens most frequently. In a normal curve, the mode is at the center along with the mean and the median. And these are the data points that are most frequently found. And notice that this curve kind of comes up to there's a term for that. Crest. Might be a crest. Or maybe that's just talking about waves. Anyways, so there's this highest point, right? That's where our mode is. And notice that either side of our normal curve begins to taper down and kind of comes close to this bottom x-axis and then extends out to the right. Those ends of the normal curve, this end over here and this end over here, while we don't see them continue, that's a terrible arrow. While we don't see them continuing on in this image, you need to understand that conceptually, these lines go on forever and ever and ever. Okay, they go on forever. They will never touch this x-axis. That's super important to understand. You're going to see how this relates to a tool that we're going to use in this class called the unit normal table later. But for now, keep in mind that these two sides will never touch this x-axis. But that also means that while we have the highest number of data points, the same data point occurring right in the middle, these values coming out to where the normal curve tapers, these areas still have data points within them that are possible. But the reason that the curve tapers down is because the further away you get from the mean, the less likely something is to happen. It's not to say it never happens, but because again, if the two lines touch, if the curve line touch the x-axis, that means something never happens. That's why it goes on infinitely. This is to say that while those data points that are far, far, far out to the right and far, far, far out to the left are extremely unlikely to occur, that doesn't mean that they never occur. Okay, so that's an important piece of information to understand as well. All right, so let's go ahead and do this. Oh, I need to erase. All right.